Hello everyone, welcome back to the lecture series of image processing and computer vision. In this session, we are going to cover a simple image formation model and how the image is forming and how the image is converted as sampling. In this topic, we cover the sampling and quantization and what are the basic relationship between the pixels and how the distance, how we measure the distance between the pixel. So in this you are going to get the clear idea about all these topics. And now let's get started. We'll see the what image formation model. Okay, in this model, how the basic image is going to form. We'll see the example, then I'll explain the topic. Okay, by seeing the screen you can understand there is a illumination source. The illumination source may be the bulb or it may be the light. Okay, so the light will falls on the object, so the illumination energy will falls on this scene. That scene is reflected, means this is a 3D image. So the illumination light falls on this scene, the scene is reflected. That reflected rays will be captured as a imaging system. Okay, so the imaging system may be the camera or it may be the any device, image capturing device. So this imaging system will capture this scene, and this scene will be converted as a digitized format. Okay, this signal, it will just simply map, this imaging system will map this reflector ray to the different levels of voltage. Okay, it will map the voltages. Okay, this is the light rays. This reflector light rays will capture this imaging system, and this image system having lens, and the lens, behind the lens we have sensors. Okay, sensors will map this light rays to the corresponding voltage levels. Okay, and this is the analog signal. So this is the analog signal, and this analog signal is mapped with this corresponding sensors levels. Okay, so after capturing this imaging system, this signal will map to the voltage level of the different voltage levels to the corresponding image sensors. After that, what we have to do, we need to convert this analog image sensor data into digitized format. Okay, digitized format. So this process, so now we are going to learn the process of converting this analog image to digitized format. Okay, so how it is going to a simple image formation model. Previously we discussed about how is image is captured with the help of the illumination source. So in terms of mathematics, how we representing the image? So image is represented in terms of f of x comma y. So here x comma y are the spatial coordinates of the image, and f is the intensity level. Okay, intensity of the corresponding pixel value. So means what, here I am dividing this is the image representation, and each pixel we can call this is a pixel, and pixel having the x and y coordinate system. So we want to know the pixel value of this is represented with the help of the function f. So f of x comma y having certain value. So this 10 is represented the corresponding pixel of value 10. So this is the intensity of the corresponding pixel, and x comma y are the coordinates of this pixel, this image system. Okay, so here what we are doing, we are capturing the 3D image to the two-dimensional system, and we represented as f of x comma y, and the values always lies, this is the spatial coordinates of the system. It is a scalar quantity. So this is the function f of x comma y is characterized by the two components based on the illumination source as well as the reflectance source. So we represented as a two functions here. Yeah, this is the two functions here. Two functions combine as a product of f of x comma y. Here f of x comma y is the representation of the intensity levels of the image, and this is I is the R is the reflectance and I is the illumination signal. Okay, this is a signal from the source of illumination. Source of illumination, it may be the sun or it may be the bulb, and that that source of light will be falls on the object will be absorb some rays, and some rays will be reflected. Okay, so this is the illumination. So because it's a continuous light, it is having the rays from 0 to infinity, but it is absorbed by the object. So R is the reflectance, I is the illumination, and R is the reflected. R is the reflectance, it is absorbed by the object. Okay, so here is a 0 is the intensity of the black, and 1 is the intensity, it is represented as a white, and this reflectance is lies between the 0 and 1. Okay, so here always reflectance is bounded by the 0, that is a total absorption, and 1 is the total reflection, and L is equal to f of x comma y. So L is the grayscale intensity levels of the particular image, and it always lies between the range between the L minimum to the L maximum. So that is the intensity level of the image is always lies between the L minimum and the L maximum. L minimum is a non-negative number and L maximum is a finite. So this is the intensity levels always lies between the that range. So if it is a black and white, the intensity levels must be lies between the 0 and 1. If it is a color image, the intensity lies between the 0 to 255. Okay, so what I want to convey here is the levels of the intensity levels always lies between the range of the particular the intensity levels. It should not be go beyond that. Next one is, so that is about the intensity levels, where 0 is considered as a black and 1 is considered as a white. Now we'll go to the main topic, that is about the sampling and quantization. Previously we discussed about the how is image forming. Image is forming with the help of the illumination source. After that will be converted as a digital format. So we want to know how the image is converted as a digital format. Here you can see on the screen we have the analog signal as well as the digital signal. What does it mean, the analog signal? Analog signal is the continuous signal which is captured at the image sensor, but that should be converted as a digital signal. How it is converting? So we have two techniques to convert the analog signal to the digital signal. So that is, one is the sampling and the second one is the quantization. So analog is a continuous, that continuous values is converted as a discrete values in terms of zeros and ones. Continuous values is like 0.1, 0.2. So like that from 0 to 1 we have like different continuous range of values. So that continuous range of values will be converted as a digitized format. That is the process of sampling and quantization. We'll see one example so that you will get the clear idea. So we have, what is our main aim is to generate the digital image from the analog image. So how we have two methods, that is sampling and the quantization. So we'll take the example of this. If you see this graph, here is the first picture is about the a 2D simple continuous image, smooth image of the image. So this is a 2D image which is a continuous image. So in this continuous image, this is a converted as a digitized format. So what is the process here? First we are taking the a line segment A and B, how the intensity varies from A to B, how the intensity changing. Okay, so actually image is the two-dimensional signal. Okay, so we have the X and rows and columns, two-dimensional signal. So we are converting this two-dimensional signal in terms of digitized format. So for that I am taking the each row, single row at a time. This is, we can call it as a row. So actually image, this is the image having the rows and columns. So I am taking the one row. So one line at a time. This one line I am taking as a one signal. This one signal is converted as a digitized format. Likewise, I'm taking the each and every line and will finally converted as each and every signal is mapped to the discrete values. So in this, for our convenience, I am taking only line segment A to B. This will be converted as a digitized format. So this is a continuous wave. So how the from A to this point the intensity is high. After that the intensity changes to low value. This is a black value. This is the white combination. If you see the screen, from A to this point it is the intensity is high. After that the intensity is varies. Then finally again the intensity values is increasing. This is the graph representation of this picture. After that what we are doing, we have to sample this image. Means what, we are dividing the entire image as a samples, equal intervals with respect to the time at a single. So this is a sampling. Sampling is nothing but the continuous data is we are locating and we are dividing the each and every point. We are dividing the entire this graph into the equal time intervals. Okay, this after converting, this process is nothing but the sampling. So converting the continuous values to the digitized format at the equal with respect to the time, this is divided as a equal intervals. After that sampling, this is a dividing the x comma y coordinate system of this. So this is the dividing the pixels with the discrete values. Then we need to assign the each pixel. Simply we are dividing the entire graph into equal samples. So this is the equal samples with respect to the time. Then after that we need to assign some values to the each and every pixels. Okay, how it will be done? With the help of the quantization. This is the process of quantization. Here we are giving some values to each and every intensity levels. If it is a white, the value will be 1. If it is a black, this is a 0. And also we have in between 0 and 1 we have different colors. Okay, each color having certain values. So we are mapping the each pixel value with respect to the colors. This is nothing but the quantization. So here finally the final version of the sampling and quantization, you will get the value. So it is in the form of digitized format, and each digital pixel having some zeros and ones values. Okay, so this is the process of sampling and the quantization. So what I am doing here is the given image is a continuous smooth image. This is the analog image. This analog image must be converted as a digitized format. For that I am taking the line segment from a single line segment in the graph, that will be converted as a signal. This is a continuous signal. After the signal, this analog signal will be divided as a equal samples. This is a equal samples. So divide with respect to the time, I am dividing the signal to the equal samples with respect to the time. I am dividing. Then that will be converted as the assigning the each sample with respect to the pixels. Okay, we are giving the some values to each and every pixel. That is about the digitized format. Okay, now you will get the clear idea how what is the sampling and what is the quantization. So you can see the definition of the sample. So after that you will get the image like this. So this is the analog smooth edges we have. In analog image we have smooth edges, but in digital image we don't have smooth edges, but each and every pixel having certain intensities. Okay, so in the top we have the thick color, but in middle we have the different color shades, the gray level shades. Okay, this is the process of converting the analog image to the digital image. Next we will see how we represent the digital images. What are the ways you can represent the digital image? So the digital images are represented in terms of matrix format. We have the rows and columns. Here we can call it as a x rows and m columns. It is starting from the 0 to m minus 1, and columns we have starting from the 0 to n minus 1. So this is a spatial domain representation of the image. So in matrix format you can represent, this is a numerical array representation of the image. It is starting from the function f of 0 comma 0. Generally image is represented f of x comma y. Here x comma y is the values of this particular pixels. Okay, this is one way of representation of the digital image. And also you can represent the digital image in terms of picture element. Okay, this is a second way of digital representation. And these are the three graphical representation of the digital image. The first one is the smooth image surface. Image is plotted as a surface. Here x is a x coordinate system and y is the y coordinate system. Means here x and y are the pixel representations, and f is the intensity at that particular pixel. Okay, this is the representation of the first format of the image. And the second one is the array representation. Okay, visual intensity of the array. You can see here, you can we have the three colors here. We have black and we have white and we have gray level. Okay, so black is represented as a 0 and white is represented as a 1. In between I am assigning the one value, that is a 0.5, that is a gray level intensity. Okay, and same thing, this image is converted as a in terms of values. Okay, same image will be converted as a values. If you give the values to this particular image, you will get the values like this, because the entire outer row is represented as zeros and inner values. If it is a gray value, it is a 0.1. If it is a color value, it is a ones. Okay, it is a black and gray and representation of the array representation. If you take any image, the digital image, if you analyze that, you will see these are the blacks. Same, this patch is enlarged. You are able to see these pixels. Okay, and each pixel is having certain intensity values. Okay, this is the digital image block representation of the digital image. If you see 0 is nothing but the black color here. Okay, if you take the value of 1, this is a 1 value. The 1 value corresponding this is 255. So generally the grayscale image having the different variations of the color. In the colors are lies between the black and white. Here is a 0 is a black color and 255 is a white color. In between also we have number of color variations, the black and white color variations. That is nothing but these are the color variations. Okay, so 119 is near to the white, that's why here is a 119. Like that the values are assigned to the image. Finally we are able to see the digital image. It looks like a smooth image, but when you enlarge that image, you are able to see the pixel values. And what are the this is a formula, how many bits are required to store the digital image. So based on the length and width of the image, so b is the number of bits used to store the image. Here n is the length of the rows and m is the columns and k is the bits. Okay, if m is equal to n, then the value the formula will become b is equal to n square k. And what are the number of intensity levels lies in is l is equal to 2 power k. Okay, here k is a positive integer. And what are the intensity levels of the pixel? So this image which is having the pixel image which consists of the pixels. So this formula is about how many bits, number of bits required to store this image. So because finally that image will be stored on the computer will store the information, so in terms of bits. So how many bits? So memory will be represented in terms of bits and bytes. Okay, so how many bits are required to store that image is this is the formula based on the length and width of the image. Okay, and the number of gray levels. Okay, number of intensity levels. These three will directly effect on the number of bits required. Okay, if the number of width and height increases, the bits also increases. If the n and m are decreases, this is directly proportional to the number of bits. Okay, so l is equal to 2 power k. K is a positive integer and 2 power k. If the value 2 power 2 means, if I take the value k is equal to 1, the value will be 2 power 1. If the k is equal to, value will be 2 power 2, means 4. What does it mean? Means this pixel can holds the 4 intensity values. Okay, got it? If it is a 8 means this pixel will able to represent the 8 different intensity values. So that is the meaning of this pixel information, and this is the formula. And what does it mean, the image interpolation? This is the one way of representing the image. So interpolation is nothing but just we are estimating the value with the corresponding present values. Okay, so why should we go for the interpolation? So this is an important method in the image processing. Here we are shrinking the image or zooming the image, or I want to do some operations on the image. This is a one method to map the existing pixel with the estimated values. We have some pixel information. Based on the pixel information, we are estimating the new values. So how we are estimating? Based on the two methods. We have nearest neighbor interpolation and we have bilinear interpolation. We have bicubic interpolation. So what does it mean, the nearest neighbor interpolation? Nearest neighbor interpolation, it takes the neighboring values of the pixel. Okay, so intensity of its nearest neighbor in the original image. Okay, so in bilinear we are taking the 4 nearest neighbors to estimate the intensity of the new value. So simply what we are doing, so if my image having the width and height as some 255 with 255, this is the size or resolution of the image. So I want to map this image with the size some 350 with 350. So simply I am zooming this image so that some new pixels will be added to the original image. Originally image having the 255 with 255. So this image will be mapped to the new resolution. So how we are estimating the new values? So this is the method. These are the three methods. With the help of the three methods, we are estimating the value. What are the methods here? Simply we are taking the nearest neighbors of the pixel. So I want to know some information about the pixel. How I can't get the information directly. With the help of the neighbors only, we'll get the information. Same thing applied in the image also. So here I am taking the 4 nearest neighbors. So I am taking the help of 4 nearest neighbors. I am taking the average of this. This is the formula. Here X, A and B and C are the neighbors of the pixel. You will get the value. That the new value will be assigned to the new image. And also in bicubic interpolation, this is the formula. And we are taking the average of the 16 nearest neighbors. Okay, this is about the image interpolation, and this is a important method to enlarge or to shrink the image, or you do some operations on the image. This is a method we are using. And you can see these are the three pictures you can see on the screen. And the first picture is about, that image is about some 72 dpi. dpi is the dots per inch. So this is a measurement of the image. So how we are intensity levels measurement. So generally the resolution of the image is represented. So this is a 72 dpi, and this is a representation of the 930 dpi. So as the intensity levels increases, you will get the clarity. Okay, if the intensity levels are decreasing, you will degrade the image. If you observe the first image with respect to the second image, the intensity is varies. Okay, so what we are doing, simply we are applying the image interpolation techniques on this image, so that you will get the clear version of the image. So based on the corresponding pixels, so we are having some pixel intensity values. Based on the pixel intensity values, we are taking the help of the nearest neighbors. So based on that, you will get the clear version of the image. This is the method we are using for the interpolation. So to fix any blurriness in the image, or to fix the edges. So in such situation, the interpolation techniques are helpful. And next we will cover the topic that is about the basic relationship between the pixels. So here we are applying some operations on the pixel. How the information, what are the relationships exist between the pixels. So once the relationship exist in the pixel, we can perform operations on the pixel, so that you will get the expected output. Okay, first we will see what are the relationship between the pixel. As we know, image is represented in terms of matrix. Matrix in the sense we have the rows and we have the columns. I am taking the same thing here. So this is the matrix, which is a 3 by 3 matrix. Okay, 3 rows and 3 columns. So here I am taking the value of P of x comma y. This is the first row, second row, third row, and first column, second column, third column. So if I want to know the information of this P of x comma y, how can you represent this? P of 2 comma 2. This is the 2 comma 2, 2 comma 1, 2 comma 3. Okay, same thing will be applied on the P of x comma y. This 2 comma 1 is nothing but this P is a information. So this is the central pixel of the information. It is having the vertical edges, vertical neighbors as well as horizontal neighbors. So these are the horizontal neighbors and these are the vertical neighbors. So these we can call this is as a 4 neighboring pixels. Okay, this is the central pixel having the 2 horizontal pixels and also 2 vertical pixels. So we can call this is a 4 neighbors of the pixel. Generally the representation of the 4 neighbors of the pixel is n subscript of 4 with respect to P. P is the central pixel. So to represent this central pixel with the 4 neighbors, these are the 4 neighbors of this pixel. This is some representation of the 4 neighbors of the pixel. And next one is the diagonal neighbors of the pixel. So this pixel having the 4 neighbors, adjacent neighbors of the pixel, as well as it is having the diagonal neighbors of the pixel. So these are the diagonal neighbors of the pixel. And so what are the 8 neighbors of the pixel? This we can call this as a 4 neighbors of the pixel, and we can call it is a diagonal neighbors of the pixel. And together the combination of the 4 neighbors of the pixel and the 8 diagonals of the pixel, we can call it as a 8 neighbors of the pixel. Means what? This is the central pixel which consists of the diagonals of the pixel as well as the 4 neighbors of the pixel. The combination of the 4 neighbors as well as the diagonal neighbors is nothing but the 8 neighbors. Okay, so these are the different relationship with respect to the single pixel. Every pixel which consists of the 4 neighbors as well as the diagonal neighbors. The combination of these two are the 8 adjacent, means it's around pixel which consists of the all the neighbors. All 4 neighbors as well as the diagonal neighbors is the 8 neighbors. So why should we learn these? Means applying operations on the based on the neighbors only, because pixels which having neighboring pixels. So I want to know the information in the image, we should know the pixel information. Based on the pixels only we can modify the data. Okay, so this is about some definitions of the adjacency, connectivity, regions and boundaries. This is also very important in the image processing. So adjacency is nothing but pixel with the corresponding the neighbors. Okay, so here I am taking the V. V is a set which consists of the intensity levels. Okay, every pixel having its own intensity levels. So based on the intensity levels you can perform the operations. So here is a V. V is a set of intensity values used to define the adjacency and the connectivity. Adjacency means who are neighbors to that corresponding pixel, and connectivity is how these two adjacent pixels are connected. Okay, whether it is connected or disconnected based on the set value V. So we are defining the V value here. V which consists of the set of values. The values are the intensity values. Okay, intensity values. Here I am declaring the intensity here is the 1. Means what? So I am going to check the values of the intensity, whether it is connected as a 4 adjacents or it may be connected as a diagonal adjacency, or we have 8 adjacency. Okay, how we can verify with the help of the set to B which consists of the intensity values. Okay, you can see the example here. Adjacency of the pixel with the range of the values which varies from the 0 to 255. If it is a black and white, values are from 0 to 1. Okay, V can be declared in the 0 and 1 range. But if it is a grayscale image or color image, the values here lies between the 0 to 255. Why I am taking the 255 always? Because previously we discussed, so intensity is lies between 2 power k. Sorry, I is the intensity which is lies between the 2 power k. So the power of k is always lies between the 2. Okay, So 2 power k is lies between the 0 to 255. And here the 3 types of adjacency we have. So we have 4 adjacency, we have 8 adjacency, we have m adjacency. I have already given the definition of 4 adjacency, 8 adjacency as well as m adjacency. You can see 2 pixels p and q values from V are 4 adjacent when adjacent if q is in the set of n subscript of 4. So this is a 3 by 3 grid format, and P and Q are the diagonal adjacencies. Okay, this is a 4 adjacency, and also we have 8 adjacency and we have M adjacency. M adjacency is similar to the 4 adjacency, but it will avoid the ambiguity, ambiguity paths. Okay, 8 adjacency means all connected, all pixels are connected, surrounded pixels are connected to the central pixel. So we have which will includes the 4 adjacency as well as the diagonal adjacency. M adjacency is also similar to the 4 and 8, but this is the condition here. The intersection of the P and Q as no more pixel, that should not be connected. The values are not from the V. If you see this example, so this is the arrangement of the pixel. So in this we have the path exist between the this pixel as well as this pixel, and also we have the diagonal path. So here is the ambiguity occurs because this pixel is connected with this pixel as well as the diagonal pixel, and also we have the connected path. So in this situation you can use the M adjacency to avoid the connectivity with the diagonals. Okay, so I am taking simply with the diagonal elements as well as the 4 adjacency. Again I am taking the 4 adjacency, just I am eliminating the diagonal path. Okay, that is about the M adjacency. And we'll see the definition of the connectivity. Connectivity is similar to the adjacent, but how the adjacent pixels are connected. Okay, I am taking the S. Let S is represent the subset of the pixel in the image, and 2 pixels P and Q are said to be connected. Okay, if there is exist path between them. So if and only if the S is called the connected component in the S. And what does it mean, the region? So region is also just simply we are simply we are taking a group of pixels are considered as a region, group of similar pixels. Okay, we can consider as a region. How these two regions are connected? If this is the one region having the similar pixels, and this is the other region. So this part we can call part is called as a one region which is separated with the other region. So all similar intensity values is considered as a one region. So this is also one region. Okay, but here is also we have 1, 1. This is how these two are connected with the Ri with the Rj. Okay, simply it is a subset of the pixel. We have the image having, when we capture the image, we are having the different regions, similar intensity values. Okay, when we capture the image image which consists of the different colors, if the same color having certain path, so then we can call it as a region. Okay, so how this region is connected with the other region, so how the relationship exists between the one region with the other region. Okay, so this is about the region. And yeah, we can take the values from 1 to k. It is k is a constant if both are connected or both are disjoint. So next one is a boundary. So boundary is how the regions are separated with the other region based on the boundary. So how the intensity will change from the one region to the other region based on the boundary. So the changing the regions, here you can see the definition. The boundary of the region R is set of pixel R that are adjacent to the pixel in the complement of R. So you can see here this we can call it as a region. Okay, how this region is separated with the other region. This is a pixel of the one information, and this is a pixel of the other zeroth information. Means it is this is a boundary. We can call this is as a boundary, and this part is called as a region. Okay, So these are some definitions of the image. Image which consists of the boundaries, image which consists of the regions, and how these regions are connected, and how the pixels are adjacent to each other. So what is the relationship exists between the each and every pixel. Okay. So this is about the boundary of the image. See, if you take this example, this is the image which is a pixel. This is a central pixel, and this pixel is connected with the other pixel. You can call it as a connectivity, and all these similar pixels are in the same region. So this part we can call it as a region, and how this region is separated with the other region, we can call it this is as a boundary. Okay. So now you will get the clear idea what is the adjacency, what is the region, what is the connectivity, and what is the boundaries. Adjacency is nothing but neighboring pixel, and what is the connectivity, how the neighboring pixels are connected, and what is the region, how the similar pixels are together at the single place, we can call it as a region. How this region is separated with the other region with the help of the boundaries. Okay, these are some basic definitions of the image. And also we have the distance. This is also important topic in the basic relationship between the pixel, how we measure the distance between the two pixels. So here is a we already know image is represented in terms of grid format, and each grid having the pixels. Here P of x comma y, Q of s comma t, and Z of u comma v. So I want to know the relationship between distance between the two pixels. Why should we calculate the distance based on the if it is a nearer, because both are very close to each other. If it is far, if it is not close to each other, based on that distance we can take the decision. So that's why we are going to calculate the distance between the two pixels. So if it is greater than or equal to 0, if the distance is greater than or equal to 0, both are at the same place. Okay, and sometimes distance are equal. When you calculate the distance of this pixel and distance of this pixels are equal, or it may be the combination, the distance of P and Z is equal to P of Q, P comma Q, and Q comma Z. These are the three conditions function for the distance measurements. What are the formulas we are using to calculate the distance? This first method, and mostly we use the Euclidean distance. It is the distance between the 2 points. Generally we calculate the distance between the 2 points with the help of the, this is the formula, x minus s whole square plus y minus t whole square under the square root. Okay, so you will get the distance between the 2 points. What is the distance between the this pixel and this pixel? And also we have the city block distance. In this city block distance, this is the magnitude. We are taking the magnitude of the 2 pixel values. Okay, so x minus s and y minus t. Okay, if the x minus s is, suppose you will get the value 1, and y minus t is the value is minus 1. You have to take the magnitude, the output will be 1. So 1 plus 1, you will get the 2. Okay, so this is the distance with respect to the city block distance. If you see this graph, this pixel information in city block distance, the values are from this pixel to this pixel, the difference is 1. Always it will be the 1. So, and also you can see from here to here, the difference between these two pixels is also 1. And one more method, formula for the distance measurement is the chessboard distance. Okay, so here we are taking the maximum of the two intensity values. So once we calculate the magnitude of this and the magnitude of this, and we'll get the value, and in this, among this, you will get the maximum value. Okay, so these are the different ways you can calculate the distance between the pixels. Okay, and this is a one way of M path between the 2 points. Okay, so this is about today's session, and thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.